Call me Ishmael. That's pretty good. We went from 1.2 megabytes to 371,000 with this bzip command. And, of course, I can unzip it, and I get back my original file. Marvelous. So how does that work? Well, it turns out on this assignment, what you're going to do is write a smaller, not quite as good version of bzip. And like magic, you will be able to compress files using your code. The specific compression algorithm you're going to be implementing is the Burrows-Wheeler algorithm, which is a three-step process, which is first to Burrows-Wheeler transform, then to move to front encode, and then finally to do Huffman compression, just like we did in class. So you may remember Huffman compression from class. Well, hopefully you do, otherwise you're going to be in trouble when you start this assignment. Counts up all the instances of all the characters in a file, and then things that occur more often are given smaller bit streams. Now that's good and well, but just on its own, it's not going to do well with arbitrary inputs. So these first two steps are going to make our files more suitable for Huffman compression than they would have been otherwise. It's kind of like this. Imagine you're trying to fold up a tent, right? So Huffman compression, this step of the algorithm you could think of as the act of taking the thing and stuffing it in the bag. Well, of course, if you take the tent when it's upright, right here, look at this thing. You try and put this thing in a bag, your bag's going to explode. It's going to be really bad. Or, I don't know, you get fatigued trying to cram it in there because you haven't taken out the posts. So, better approach, take out the post first, squeeze out the air, and then and only then, stuff. So let's go through the hows, and we'll get to why later. So how do we do a Burrows-Wheeler transform? What we're going to do is take a string, let's say weekend, and we're going to permute it in a very specific way. So what we're going to, in order to find that permutation, we first form a list of all of the suffixes if we treated the string like a circular string. Okay? Well, let me give you an example. So the first the 0th suffix is weekend. Next is we pretend like we rotate this whole thing to the left a little bit, and we get, say, ekend w. So just rotate it around and treat it like it's circular. Then we get ekend we, then kendwe, and week, and weeke, and finally dweeken. All right. So we form that suffix array. That's the first part of Burrows-Wheeler transform. The next step after we form the suffix array is to sort them, right? And we just treat them like a string. So the first one's going to be dweeken, right? So it starts with the D. Then we have all the ones that start with E. So let's see. The first one in this order is ekendwe. Then the next one is ekendwe. And next comes endweek. Okay. Next up comes kendwe, then endweeke, and finally weekend. Okay. After forming the suffix array, sorting it, we do the final step, which is to return the final character in each of the sorted suffix array, along with a number telling us where the original string ended up. Okay. So what we'll end up doing then is we say, okay, the last character of each string is nwekeed. Right, N-W-E-K-E-E-D, and we'll prepend a number corresponding to where weekend ended up. All right, so where did it end up? In the 6th position. And this right here is the Burrows-Wheeler transform of our original string, a permutation along with a number saying where the original string ended up. So our poor little Nwekeed might ask us, why have you tortured me so? Like, we've just completely discombobulated him. Well, our goal with our string, turning it from weekend to nwekeed, is to make it easier to compress, as I mentioned. And in this case, it's not going to help. But if we look at the example on the Burrows assignment page, we see that if we take the string abracadabra and we do the same operation on it, we end up with something where there are a lot of A's in a row, which is going to make it easier for us to ultimately compress things. Now, of course, using the Huffman compression algorithm, it doesn't matter what order things come in, right? That should be, hopefully, comes to mind very quickly, because every character still occurs the same number of times that it did before we permuted. So we got to do something else before we can take advantage of this structure, these repeated characters. And that's the move to front encoding process. Let's go through an example of the move to front encoding process to explain how it works. So let's suppose I want to apply move to front to this string gh, no, whoops. To do this, the move to front operation, we keep a local copy of our alphabet or aside, And it begins just in the normal order. In this case, we have a 36-character alphabet. And we are going to convert this thing by looking up the position in this array of the letter we're considering. So in this case, G is 0, 1, 2, 3, 4, 5, 6 characters long. Okay? And then we take that character of the alphabet and move it to the front. Right? So next comes along H. Where's H in this process? Well, or in the alphabet, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so H gets moved to the front. Okay, here's H. All right, next up, here's G. Where's G? He's in position 1. Okay, so we'll move G to the front. And now we have H. Where's H? Position 1. Okay, good. Okay, so we'll move that to the front, and so forth. And so we'll keep moving H and G back and forth to the front, and eventually we'll get that. And I guess the last one that gets processed is H, right? So next along comes this letter N, and we say, where is N? Well, N's going to be, in this case, 10, 11, 12, 13 positions along, and we'll move N up to the front. And then comes O, which is going to be now 14 positions along. And then N comes along and is 1, and gets moved to the front. Oops. And then O comes along, and that gets moved to the front. Okay, and so that, of course, will repeat this many times. All right. Finally, we get up to W, and W is going to be the 22nd. So we put 22, and we move her up to the front. Next comes X, and X is going to be now 23. So he goes up to the very front as well. And then we'll alternate again as we did before. 1, 1, 1, 1, 1, 1. Okay? So if we observe what happened, we started with something with 6 different characters up here, which all occurred with roughly equal frequency. But after doing move to front, oh my goodness, this 1 happens a whole lot of times. And that is good news for Huffman. So Josh, wooks is really easy to compress. Why should I care? Good point. Why do we expect this kind of process to work for real text? Well, let's think about what happens when we take text and run it through Burrows-Wheeler transform, then move to front. So I'm just going to make up a small little example. Let's consider the 3-letter sequence hen. So I'm going to observe that in English, typically that's preceded by W or T. Maybe some other letters I'm not thinking about. I mean, for example, Chen. But I'm going to discard common Asian surnames to keep our options restricted. So if we think about what happens when we form all the circular suffixes for a text, so say Moby Dick, I form 1.2 million circular suffixes, 1 for each letter of the book, and I get, let's say, hen, T, jar, space, ato, T, hen, W, hen, T. These are obviously not in order. Otherwise, they would need to be, you would see the same letter creeping along. So we have a whole bunch of circular suffixes, and when we sort them, right, as we must for one of the steps of Burrows-Wheeler transform, then what we end up with is, well, let's sort all of these, and we end up with something like, in this case, the Ado goes up here, jar gets moved out of the way, and these get moved, and so forth. And again, I've omitted some of them. But what we'll observe is every single time hen in Moby Dick occurs, then the letter immediately preceding hen is at the end of that same circular suffix. So that means if there's only a limited number of letters that occur before hen, they're going to all get clustered together. So what we'll end up with, let's just say, let's throw in the Han Chinese surnames. Maybe I get C. Maybe there's, it's Moby Dick, so the word then probably occurs a few more times. Kind of a long book, but an amazing book. It's super good. Then what we'll get is a whole bunch of C's, T's, and W's. And as you can imagine, right here, even if we have, 7 or 8 different letters that precede hen, they're going to be a fairly restricted alphabet set. So when we call move to front, we're going to get a ton of zeros, corresponding to every time we're just running through all the zeros, T's, or W's. That's the entire compression algorithm. Transform, encode, and now compress. So we'll talk about the decoding algorithm in a little bit, but first I want to focus on the key implementation details you'll need to think about as you go. The transform, it turns out, is fairly tricky as of the most recent releases of Java. In the old days, things were fairly straightforward to do this. Let me explain roughly why you're going to run into trouble. Let's suppose you're compressing Moby Dick. That means you need to create 1 million suffixes, each about 1 million characters long, and then sort them. So if we form all of those strings explicitly, obviously that's a terabyte of memory, and that's just not going to work in this current era in civilization. So if we want to actually compress things, transform, we're going to have to be a little more clever. And as I alluded to, the old days, that was fairly easy with something like this. So in is the length of the text. Then I do this clever trick where I say, don't worry about what this means because it doesn't apply anymore. And then I would say, okay, let's create an array of suffixes, new string of length n, or new array of strings of length n. And then for each, then let's just create all the substrings here. I plus plus, si equals text.substring I to I plus n, or something roughly like that, and then just arrays.sort s. Okay? So in the old days, when substring was very fast and used constant memory, then this was perfectly fine. But if you try something like this, you are going to have a quadratic problem, which is very bad to be quadratic, say, in the length of Moby Dick. That's just, as I mentioned, a terabyte of room. So what we're going to do instead is we are going to create a helper class, which is called circular suffix array. And this is the very first thing you should do for the assignment, is to write this class. So what does this circular suffix array class do exactly? Well, the core idea is relatively simple, and I'll explain by example. So if we look at the API, we can pass a string to it, and then it has some method called index. So if I create a circular suffix array for the word weekend, then what it should do is support index queries. And how that works is, all that means is when I say, hey, what is the index of 0? It's supposed to tell me, effectively, if we pretended like we had the sorted suffixes array, where would dweeken, which original string did that correspond to? So if we say, what's the CSA index of 0? That is 6. If we ask, for example, what is the CSA index of, I don't know, say 3 here? Then that is 4, right? So the third sorted suffix corresponds to the fourth unsorted suffix. So this leaves a couple of questions. One is, why is this useful? And two is, how do I implement this? The reason this is useful is that it avoids the need to actually form the suffixes array. So for example, if I create an object like this with this line of code, I'm going to claim that knowing that CS index 0 equals 6 is just as good as forming the circular suffix array. So there is a way to take this information and get back the letter n. All right? And so I'll leave that to you to think about a little bit, but it's not too bad of a programming challenge. That brings us to our other question: how do I implement this class? So I'm going to point you to the checklist. If you look under the possible progress steps, here when you try to implement the circular suffix array class, the main suggestion to keep things very clean is to consider creating an inner class for a circular suffix array called circular suffix. And I think taking that approach should result in code that I think won't be too painful to write, and even though it may not be the most efficient code, it will meet the requirements and it will get you going. By contrast, the move to front part of the process is relatively straightforward to write, and so that's the entire encoding sequence. That should be enough to get you started on the assignment. Definitely, if you're feeling at least at all shaky in this class, pay close attention to the possible progress steps in the checklist. You should certainly start with circular suffix array and make sure it works before you do anything else in the assignment. Do that. At that point, then and only then move on to the Burrows-Wheeler transform method using circular suffix array and make sure that works. And after that, I would recommend moving on to the decode process, which will be described in the next video.